Hi there, this is another training video. Today we're going to talk about the introduction to PID controls specific to the CPC control system. And this is one of those concepts that most control engineers know a little bit about, but not a lot about. And so I'm going to go through kind of how, what is a PID, how it's used. We're going to, if we look at the screen here, let's click here. Okay. We're going to talk about what is a PID, basic terms used for the PID, explanation of P, I, and D terms themselves, what the proportional band is and how it's used, the reset, how that's used in the integration, and band offset, and also some different considerations for when you tune the autoclave, okay, or oven in that case. So what's a PID? PID stands for proportional integral derivative, and it relates to the control loop feedback mechanism, or controller, commonly used in industrial control systems. A controller that uses PID is named a PID controller, and within our CPC control systems, we utilize a specially configured output. It's actually called output underscore PID, and that's what we use to control temperature, pressure, vacuum, and most of the time we use PIDs for proportional control of these items. We typically don't use them when we're doing on-off control. Okay. So let's get some terms straight. We're going to, as a controls engineer at ASC, you're going to hear the words or the term set point, process variable, PV, output, error, and that type of thing. So set point is the control target for the PID controller. So for temperature, for instance, this would be the temperature setting. For pressure, it would be the pressure setting. It is often abbreviated as SP, and throughout this training, you're going to see SP on a lot of the charts and diagrams. Process variable, that's the actual sensor value being controlled by the PID controller. It can be a temperature, pressure, flow level, or really any other sensor that you're controlling. And we call that PV sometimes. So in control terminology, there's an SP and a PV. The output is the actual output of the controller or of CPC's PID output. In most cases, this is a 0 to 100% signal. It is often abbreviated as out, and in our control systems, that output is typically routed, either separated and routed to a heater, to a cooling valve, to a pressure valve, to a exhaust valves. So that output is what is used to actually drive those physical elements. Error is the difference between SP and PV, and it's actually SP minus PV, and in conventional PID algorithms, and also in a lot of individual controllers that you'll find on the market, that the error is unitless, or it's in percent. In the CPC terminology, that error is always in the units of the measure of the PV. So if you're controlling temperature, then error is going to be in degrees Fahrenheit or degrees Celsius. Error is abbreviated as E. Okay, so here's your two different diagrams. Typically here you are. PID controller takes a set point, takes a process variable, compares it, and then spits out a controller output to the process. And the process would be the actual cooling valves, heating SCRs, and basically that then changes the actual process variable, which comes back through a sensor back to the PID. So we consider that to be a control loop. Okay, and what's actually going on underneath that PID controller is the set point is compared to process variable. It's subtracted. There's an error generated, and that error is then used to determine a P term, an I term, and a D term, which are all added together to give you your control output. Okay, so that is a classic PID diagram there, and the basics are P, I, and D. P is proportional, which is the output. The output contribution is derived from the error, or the instantaneous error at time equals X. I is the integration, and that's the output contribution, is derived from the amount of error over time, okay? And basically, it's the area between the set point and the process value. Derivative, that output contribution is derived from the change of error over time. So it's basically the slope or the ramp or the rate of change of the error, okay? So this is your classic PID calculation. I pulled it off the web. In the classic PID, what you'll notice is the gains constants K, and there's KP, KI, and KD, are applied to the error integral of the error and the derivative of the error. And here's your integral symbol, and here's your derivative, which is basically change in error over change over time. Okay. Now, so basically the proportional term P. So in a P controller, which is a controller which only uses the P portion, the output is derived exclusively from the error. Okay, so this is used for processes with no losses or disturbances. You can kind of think about this as, let's say, filling a pail full of water. You know, as you fill the pail and the water comes up to a given set point and you shut it off, it's going to stay there. There's no leakage. There's nothing. There are no losses, and P can actually do a pretty good job of controlling that, because as you come closer to the set point, here you see as PB comes closer to the set point, error drops, the output drops, and then we basically fill the pail up. I integral. Okay, when a process has losses, you need I, and you need integration. The integral of E, or error, is the area between the set point and the process variable. So as P converges to 0, so here we have so PV is approaching set point here. So the output due to P, or due to the proportion, is going to converge to 0. But if I have losses in the system, that is not enough to keep me at set point. And so what occurs is we start integrating this error here, or which is the integration, or the area under the set point and above the process value. That gets integrated, and that integration results in an I term increasing. And basically the idea is that once P converges to 0, I has increased to a point where it maintains the set point. It maintains PV at the set point, okay? And this would be a perfect control solution here, where there's just enough E integrated here that adds up to just the right amount of I, which keeps it at set point. Derivative is a different term. When a process is expecting a large disturbance, you'll need a D. D is linked to the rate of change of error. So when error changes due to a disturbance, D provides that extra boost of output to counteract that change. So now, frankly, ASC rarely uses D in our controllers. Usually most control engineers put in a D, and they shouldn't. And I'm not talking about control engineers here, but elsewhere in other companies, they just always want a P and an I and a D. But the D really is only used for kind of unique situations. For example, let's say you're controlling a small oven and someone opens the door very quickly and shuts it. You're going to end up with a disturbance like this, and the D term can quickly jump up and add an extra boost of heat. Which you're not going to get with the P, right? Because P requires a big error to give a lot of P, and you're not going to get it with I, because I occurs over time. It's the integration of the error. So D is that sort of kickstart or boost which occurs when you need it the most. But autoclaves don't have that, because we come up to temperature and everything's stable. Even ovens, no one's opening doors in the middle of the cure cycle. So we typically don't put D in our systems. Let's talk about proportional band. So the proportional band, or we call it PB, is an alternate method for sizing and determining KP, or the proportional gain. And on the classic PID, you have error times KP, which is the proportional gain, equals that P term. Now, the proportional band, so in CPC, we use a proportional band rather than use a KP term, okay? And the proportional band is in units of the process value. So in a temperature example, here we are at 250 degrees, proportional band would be sized based on a certain temperature. And so here I've sized a 20 degree Fahrenheit proportional band. And it basically defines the range of the process range, which will derive a 0 to 100% P term. Okay, so in most of our cases, the 100% is at the bottom of the band and 0 is at the top of the band. Okay, and here's the calculation: P equals error divided by PropBand times 100%. Okay, so E is in degrees F in this case, proportional band is in degrees F. Those two units cancel each other and we end up with percentage. Okay, so with an error of 20 divided by a proportional band of 20, that's going to give me 100%. And with an error of 0 divided by a proportional band, it's going to be 0%. Okay, and so with when the process is inside the proportional band, you will be proportioning. It'll be between 0 and 100%. Outside of the proportional band, down here, P will be 100%. It'll be clipped at 100. Okay, so now it's interesting to note that the prop band, and that's actually should be a P. The prop band is the inverse of Kp. Okay, the larger the band, the lower the gain. Okay. Now we'll talk about reset. Okay, so in many industrial PID controllers, the Ki term, which is the integral gain, is referred to as reset. And I don't know how it came up that everything is called reset, but it is called reset, and we adopted that term within CPC. So our CPC reset is actually in units of percent per error per minute. Okay, and this can be described as percent per deviation per minute too. So when you're explaining it to someone, and basically what it means is we're going to look at the deviation of process to set point, which is the error, and we're going to take that area or over time, and that's going to be your integration. And basically CPC's integral is calculated each and every scan based on the amount of scan time. So if the scan time is every 50 milliseconds, every 50 milliseconds we're going to take that portion of area, and that's going to be added to the integration or to the integral term. And obviously, if the error goes negative, which is when PV is greater than set point, then the integral will reduce, and so we're either adding to the integral or we're subtracting from the integral. And this is the actual calculation here, which occurs. And it's important to note that that integration within CPC's PID will only occur inside of the proportional band. So if I'm outside the band, this way or this way, we will not integrate, and it will zero that integral. Okay, and the reason for that is if I have this huge error, I don't want to keep adding a huge amount of integration. So we basically start integrating when we come close to set point, which is typically within the proportional band. Okay. Now let's talk about some considerations for reset. So basically, reset is the multiplier that's going to be multiplied by this area to determine the amount of integral which is added each time span. Okay, so CPC's PID integration only occurs inside the proportional band. As I said, when the PV moves out of the band, the integral is zeroed. So you need to remember that. It makes a difference. You might have an integral and all of a sudden it goes to 0 and you don't know why. That's going to be why. Once inside the proportional band, the integral will build up or build down based on the calculation deviation from set point times time in minutes times the reset value. Okay, so this will be calculated every scan interval. So it's the deviation times the number of minutes times the reset value. Because integration occurs inside the proportional band, when the proportional band is changed, meaning you resize the proportional band, this will actually affect the amount of integral that gets built up. Because if you increase the proportional band, then we're going to start integrating earlier as the process approaches and as the process value approaches. So they are not mutually exclusive. They are basically linked together. So if you increase proportional band, you can expect to have more integral added, and you might have to adjust integral down or adjust reset down to bring about a smaller integral. Okay. Let's talk about band offset. So in the previous example, we had a set point, and our band, our proportional band, was basically positioned where 0% was at set point and 100% was down here. Okay, but in our applications, CPC applications, we typically control both the increase and decrease of process value. So we could be heating and cooling. We could be inletting and exhausting as far as pressure. So we need to shift the proportional band upward so that it proportions on both sides of the set point, okay? And this shift of taking that band from the set point and shifting it up, that is known as band offset, which is in units of percent. So this is called when we do this, we're actually creating, when we shift that band up and position it as a centered on the set point, that is considered a split range PID at that point. And here's the calculation when we put in a band offset it's the normal P equals E divided by PB times 100, but then plus the band offset, okay? And you can see here, so I've taken a 40 degree F proportional band and shifted it 50%. So now 50% is here. The PID output band is basically shifted by 50. So at set point, the PID will be, at least the P term will be 50%. And when we do that, we kind of identify a range of heating and cooling for that PID. So at 50%, we'll have no heating, no cooling. Above 50%, we'll have cooling, and below 50%, or sorry, above, as we come down, 100% is going down. So from 50 to 100, we're going to have heating from 0 to 100% heating. And above the band, 50 to 0, is going to be 0 to 100% cooling. For example, it could be, if we're doing pressure control, then this would be inlet and this would be exhaust. And so you can see that we're taking one band and we're kind of splitting it into two regions, and those regions are either handling heating, cooling, inlet, exhaust, vacuum, venting. It really depends. And each of those portions or those regions can be further calculated. So heat percentage equals that P term or that output minus band offset times 2, and heat and cooling equals the P minus band offset times -2, or if P is the output, it's the same thing like that. So it's important to note that all CPC systems, for the most part, the PID outputs are almost always using band offset of 50%. This basically centers the proportional band on the set point and creates a P zone of a half a proportional band below the set point and half above the set point, okay? Inverting the prop band. There are some cases, usually when we're controlling a freezer, where we want, rather than 100% being heating, we want 100% to be cooling, okay? And in that case, we're going to want to basically flip that proportional band, okay? And to do that within CPC, you just have to give that proportional band a negative value. So in this case, I have a negative 50 degree, and that inverts it so that P is up here at 100 and down here at 0, which before this was 100 down here and this was 0. So here's your typical PID within CPC. We call it the output PID class of object, and this is telling you which of these parameters or properties represent the properties that we've discussed in the training. So feedback is usually pointing to the process value. Proportional band is called PropBand, and that's in units of the feedback, in this case degrees Fahrenheit. Reset that's that Ki integral gain, and that again is percent per degree F per minute or percent per PSI per minute. The rate is the KD derivative gain. So rate is, this is again a term used by other PID controllers.
rate is the KD, or derivative gain. And because we don't use derivative, this is almost always 0, so you don't have to worry about that. Band offset 50%. And then here's the error that's being displayed, and then here's your integral, which is the I term. That's the amount that has been added, okay, over time. So some considerations for the proportional band. The process momentum, so depending on what we're controlling, the process will either have momentum or won't have momentum. Okay, so process momentum is a key factor in thermal processes and less so in pressure and flow. So thermal processes tend to have momentum. If you apply heat and then you turn off heat, the process keeps driving up because you have a lot of kind of thermal momentum within the system. And when you're setting the proportional band, when you're sizing it, you should think about how much momentum there is in this process, and you'll want to size that proportional band large enough so that as that process, or as that PV moves into the proportioning zone and it begins to kick back, it will not overshoot set point. So if I have a small proportional band and I'm heating at full heating, 100%, and then I only have a small region to slow down, then it's going to fly over set point. And so normally we don't want to size it that way. We want it big enough, even with its band offsets, so that as I approach, my momentum is going to be used up within the bottom of the proportioning band. And then the best solution is to come just slightly below set point with my P term, and then my I term can kind of add or subtract the small amount necessary to stay at set point. Okay. What's another consideration? Keep your reset low. Reset is the integral gain. If you have a very high reset, what's going to happen is if you're below set point, you'll integrate that error, and it'll add to the output value, which is the I term contribution, which will then heat too much and you'll overshoot. Okay, and then you'll have error on the top, which will then subtract quickly, and then you'll go into full cooling, and then you'll go into full heating, and then you'll go into full cooling, and you can reach a instable or an unstable condition here, instability, where you basically are oscillating higher and higher and higher, and that is due to having a very high reset. So it's a good idea to keep reset low. It's be conservative. If it's too high, it will tend to give you problems. We're gonna kind of play around a little bit with that. But most of our systems, we're looking at ranges of 0.2, 0.1 to 1 as a reset limit. Avoid windup, which is and the answer is 0 your integral. So in cases where the control loop is disabled, for instance, when you're at ambient conditions and the autoclave door is open, we don't want to be heating, right? So the actual control loop it's still running, the PID is still running, but I can't really do anything with that output value. So what occurs there is, so here's a case where my autoclave door might be closed, or open, but due to some calibration error, there's a small error between set point and my process. So pressure and set point, small error. Well, over time, it could be hours and hours. There's that PID, it wants to integrate that error, and it's going to slowly increase that integral value over time to the point where it'll go all the way to 100%, even though I'm very close to set point. Okay. Obviously, we don't want that, because the minute that you turn once you shut that autoclave door and you enable pressure, it's going to have this huge integral, and it's just going to pressurize super fast, and that's not what we want. So what we do in those cases where we are disabling different modes is we want to zero the integral while it's inactive, and then when it becomes active, then we allow the PID to, or the I integration term to add up. Okay, so that's basically nearing the end of this end of this training session. This is a example calculation, because you're going to want to get good at sort of on the fly figuring out how much integral is being added or what the p term is at a certain time. So this is just a very simple example. I have a prop band of 80, a band offset of 50, and a reset of 0.2. And the scenario is air temperature is hovering 10 degrees below set point. Okay, what is the p term? What's the heating output, and what is I increasing by? Okay, I is the integral. So what's the p term? Well, p is again the error divided by proportional band times 100 plus 50, okay, plus the band offset. So I can say, okay, 10 divided by 80 is 0.125 times 100 is 12.5 plus 50 is 62.5, which tells me immediately what the P portion or P contribution of my PID is going to be at that time. Now, knowing that that's a split range, 62.5% PID output does not necessarily mean 62.5% heating or 62.5% cooling, because those can be further calculated by subtracting by the band offset, multiplying by 2 or -2. So in this case, the heating output would be that value minus 50, which is 12.5, times 2, which is 25%. So you should get good at kind of looking at this stuff and quickly trying to figure out what that output would be. Now, if I remain hovering at 10 degrees below, I've got an error of 10 degrees, and over 1 minute, that area is going to be 10 times 1, 10. And then if my reset is 0.2, I multiply that by 0.2, and I get 2% added to my integral per minute, okay, in 1 minute, because it's integrating that error, multiplying by that reset, and adding that to the I term. So although my PID for the P term is 62.5, every minute now it's going to be adding 2% more to that. So after 1 minute, it would be 64.5. After another minute, it would be 66.5, and so on. Now, obviously, as I add more percent to my output, I expect that my error will slowly reduce, which will reduce the P term, and it'll reduce the amount of added integral. And the idea is that as P approaches set point and converges on 0, the I has built up enough to stay at set point, right? And so that's basically how that works, and that's the introduction to PIDs. Hopefully that gives you a little bit more understanding of that, and there'll be a test, and good luck. Okay? Thanks. Bye.